Hello everyone, this is Katayoon Sheikhi. Today I am here to discuss a subject that explores motor control with focus on achieving an efficient regulation of motor speed. My research study is titled as Advanced Adaptive Nonlinear Speed Control System for DC Motors using PID controller, with details of designing and implementing a speed control system for DC motors. This research is a contribution to the field of motor control and has implications for various industries that rely on accurate speed regulations. This is a course ENGI 9857 Instrumentation and Control of Energy Systems in Memorial University. The instructor is Professor Mohsen Jamil, and this is for a spring 2023 semester. Before we go through the implementation and simulations of MATLAB, we go through a brief introduction to motor control and PID controllers. Applications of DC motor controls in daily life is shown in the picture below. The DC motor application in different sectors such as elevators, vacuum cleaners, trains and lift tracks and solar panels and many other things. Motor control is a fundamental aspect of numerous industrial applications. The influence of DC motor applications in daily life cannot be denied. DC motors have applications in automobile, home appliance, industries, and almost everything that requires movement, where maintaining a consistent speed for a DC motor is of paramount importance. To set the stage for a study, this paper provides an introduction to advanced control techniques and the operational principles of DC motors. Here we have the definition of controller with feedback. A feedback controller measures the output of a process and then manipulates the input as needed to drive the process variables toward the desired set points. Here in this figure 2, we have the block diagram of a control system with feedback. The YS is the output, the US is the input, and G1S is the system, and G2S is the feedback. As we can see, the G2S measures the output and it changes the input as needed to get the desired results the system needs toward the set point that is provided. Here we have the formula which is provided here, and it's a simple form of the feedback connection. And now, moving toward the definition of PID controller. The heart of the control system lies in the proportional integral derivative, or PID controller, which continuously corrects the error between the desired speed input and the actual speed output of the motor. A PID controller, short for proportional integral derivatives controller, is a feedback control system, commonly used in engineering and industrial applications. It helps regulate a process by adjusting a control input based on the differences between a desired set point and the current process variable. Here, as you can see in the block diagram of PID controller, we have three different sections in PID controller. First section is proportional, or P term. The controller response is proportional to the current error differences between set points and process variable. It provides a fast and quick response, but may lead to oscillation if it used alone. Second component is integral, which we can see it with I term. This term accumulates the past errors over time, helping to eliminate steady state errors that may occur with only the proportional term. It brings the system to the set point over time and helps mitigate the offset. And the last term is derivatives, which is D term. The derivatives term considers the rate of a change of an error. It can help dampen the system's response and reduce oscillations, enhancing the stability by tuning the three terms P, I, and D. Engineers can achieve the desired trade-off between responses speed, stability, and a steady-state error. PID controllers are widely used in various fields, from temperature control in ovens to speed control in motors. Here we have the control law, which we can see here. And this control law is used in various points when designing a control system. Okay, and moving on, here we have a figure of a PID controller function, and here we can see how it works. Here in this block diagram, if our desired speed is 10 kilometers, as you can see here, and we want to get to this speed, when the system starts working, we have a rapid change of speed, which gets to 12 kilometers. And here we have an overshoot before the system gets to a steady state. And the time before when the system starts and until it gets to the steady state, we call it the transient period. And the PID controller function is to shorten this transient period and makes it near to zero to enhance the system's function. And here we can see the different parts of the PID controller: the transient period, the overshoot, which is between 10 and 12, and the steady state. The steady state might have some time to get to the 10 kilometers. It may get to 9 or 11 before it becomes steady at last. And as we said before, the objective and the primary objective of this research is to design a control system capable of maintaining a constant speed for a DC motor, even in the presence of disturbances such as load variations. The paper presents an advanced methodology that has several key steps. Here in this figure, we have our MATLAB simulations. We have motor modeling, which we can see is the DC machine. The DC motor is comprehensively modeled, capturing both its armature and mechanical components. This model enables a deeper understanding of the motor dynamics, aiding in the subsequent control system design. We have IGBT here, and we have a gate and a series of RCL branch. We have a diode and a DC voltage source. And we have a bus selector to see the speed, and it has variables to get the output. And then it comes to the PID controller, the speed control system, and then we have a slider gain which references the input, and we can change to get our desired results from the simulations. Here we have a scope here, which we don't change in the MATLAB. We don't change its variables, and then we have a voltage source, which is 300 volts here, and the voltage is constant, and we don't change that, and giving the result. Okay, and here we can see the simulation results, which are impressive, and it sheds some light on the effectiveness of the proposed control system. In the initial and first simulations, which you can see in figure 7, the simulation results were 3 seconds and without input change. The response to sudden the speed we can see is settled at a desired value of 700 rpm with minimal overshoot and fluctuation. The system here demonstrates its ability to stabilize the motor's speed within a very short period of time. Okay. Um, we have 4 different simulations here. The first one is speed. The second one is armature current, and we have field current, and we have electrical torque here. And here you can see the armature current and the electrical torque are very similar when it comes to the results. Okay. Here in the second simulation, the controller's response to sudden speed changes is examined. Here we have in figure 8 the simulation results for 10 seconds and 4 times input changes. The PID controller here tries to settle the speed to find the steady state, and it is obvious that the reaction of the PID controller is very fast. When we increase or speed up the PID controller, it has an overshoot, but on the other hand, when we decrease the speed, there is no overshoot at all. But the time it takes to reach the final value is much more than the time when we increase the speed. The PID controller showcases its ability by promptly and quickly adapting to changes in the desired speed, minimizing the overshoot and the efficiency settling in the system. These graphs presented in this slide illustrate the controller's swift reaction to these disturbances. In conclusion, this paper presents a comprehensive study on an advanced adaptive nonlinear speed control system for DC motors, employing a PID controller. The research highlights the efficiency, accuracy, and robustness of the proposed control system in the maintaining a constant speed, even in the face of load variations and sudden speed changes. This study holds a significant promise for a wide range of industries that rely on precise motor control, from automotive applications to industrial machinery. The integration of advanced control techniques, nonlinear modeling, and PID controller provides a robust solution to a long-lasting challenge. And as we move forward, the findings of this research have the potential to change the way we approach motor control, paving the way for enhanced efficiency, reduced energy consumption, and improved performances across various sectors. The implications of this research are not only limited to the DC motors alone, but they can extend to the broader field of control system and automation, ultimately shaping the future of industrial technology. Thank you for your time and listening to this video. If you have any questions, I would be really grateful if you leave a comment or an idea, or if you have any suggestions, and leaving them in the comment section below this video. Thank you so much, and I hope this was useful for you.